Hello all, this is a video solution for group work F2, which deals with simple harmonic motion and the equation that is used to illustrate simple harmonic oscillators. Okay, the top 5 questions deal with a sample question that we did together in class. I don't have my Apple Pencil with me, so I have a different type of stylus. It's not as good, so I hope I don't have to write. All right, the period for this problem is represented with the letter T. So we have all of these symbols up here. So the things that really matter for the equation that relates position and time for simple harmonic oscillators are these ideas. A for amplitude, this lowercase f for frequency. A capital T represents the concept of period. A lowercase t represents time. And this funny looking W, which is the Greek letter omega, represents angular frequency. And then a couple quick reminders that frequency and period are inversely proportional. So if you have F, that's 1 over T, and T would be 1 over F. This is an equation that comes from your equation sheet. Angular frequency, well, the format on the equation sheet has T here and angular frequency here, but both are true. Angular frequency is equal to 2 pi over T, or angular frequency is equal to 2 pi times F. Both of those are true because these are inverses. Now the units for angular frequency are radians per second. And then moving back to the left side, this is literally the equation from the sheet. Position is equal to amplitude times the cosine of 2 pi times the frequency times time. So if you rearrange it to include it for period, so the t can be in the denominator instead of frequency in the numerator, this is another way of writing this equation if you only have the period. But then if you recognize that both of these, 2 pi f or 2 pi over t, those are equal to angular frequency, this is the simplest way to write that equation. The position of an object oscillating on a spring is equal to the amplitude of that oscillation times the cosine times the frequency, angular frequency times the time. So this is a review and demonstration of how those equations can be rearranged to be helpful in this format. So the question is, what is the period? So if the format looks like this, that's 2 pi over t, this whole, if you solve for this value, 2 pi divided by 0.88, that would give you an angular frequency. But the 0.88 is the period. That's the t from the equation up there. The amplitude comes from the front of the equation. That's the coefficient, really, for this entire process. Now, angular frequency is this whole quantity solved for. So 2 pi over 0.88 is 7.14. And again, the units are radians per second. And the question is where is the mass at t equals 0.25 seconds? I don't know why I drew it this way. But if you substitute the value 0.25 in for that t, you would solve for the equation where it is x equals negative 1.38. This is a question that you do not have to be able to solve for on your own. It would be provided. You do not have to do calculus to produce this, but basically that's what's used. Calculus shows us that the derivative of the position equation is the velocity. So you don't have to be able to do this. I am providing it here though, if you'd like to try. Okay, so the next couple questions all relate to a separate problem, so it's using the same ideas and applying it in a new situation. So the problem says that you have a simple harmonic oscillator with this frequency and this amplitude. So here are some of the other properties of this. The mass is 0.75 kilograms and the spring constant is 13 newtons per meter. So if you ever have a problem with a bunch of variables listed all in the problem, that's the first thing you should do is write them down. So the frequency was given, and because frequency and period are so closely related, it's really easy to calculate that one right away, and you probably should. It's just the inverse. So 0.667 is the frequency, so 1 over 0.667 is the period. The amplitude is given, the mass was given, and this spring constant is the letter K that was provided, so that's 13 newtons per meter. Okay, so right away the question says, what is the period? Well, if you understand that these are related and you do it already, if you do it right away, you actually solved for the first question before even seeing it. So period is 1.5 seconds. The angular frequency is this, remember this is omega, and it stands for 2 pi divided by t. So, or you could do 2 pi times f. Both of those are possible to use, but regardless, whichever one you pick, you will get the same answer. It's 4.19 radians per second. So the third question asks you to write an equation for the object's position as a function of time. Now, this is just basically what you would show in any type of log or pro experiment where you have position is equal to amplitude times the cosine, and then times the quantity of the angular frequency times the time. So you could write it either by displaying angular frequency or by displaying frequency, but regardless, it should be 7.25 centimeters times the cosine times these quantities, either 4.19 radians per second times t or 2 pi f times t. So that when you substitute 0.25 in for t, you can solve for the equation where x equals 3.6 centimeters. In the second question, it asks you to substitute 0.5 in for t, and you end up with x equals negative 3.6 centimeters. So the last thing to think about before we do question 6 is that let's look at the position over time. So if this is time 0, let's see if I can pick a different size. All right, so if this is 0, and we'll make this the 1.5 seconds, the object is going to oscillate from here all the way down, and it will return to its peak at the completion of one full period. So if you track the motion of the object for that time, let's see if these quantities make sense. So if you were to split this 1.5 period into halves, this is where it should be at 0.75. And then this could be split into thirds, 0.25, 0.5. And so the question is, like, at 0.25 seconds, where is the object? It's at roughly half of the positive amplitude. And then at the 0.5 mark, it's at roughly half of the negative amplitude. And at the 0.75 mark, it's at halfway through the period, which means that if it starts at an amplitude of 7.25, it should be at negative 7.25 when it's halfway through its motion. So if this object's position after 0.75 seconds is then substituted into this equation, you would show that the amplitude, or the position, is actually equal to the amplitude, which is negative 7.25 centimeters. Okay, we did not solve for questions 7 and 8 in class, so we can work on those some other time. But if you have any questions about this group work, feel free to come and find me. Otherwise, good luck studying for your test.